Welcome to the lecture session on differential equation. Today we are going to discuss various applications on differential equations. One of the application is the LCR circuit. In the LCR circuit, we have R for the resistance, L inductance and the capacitance, and the circuit all of you will be knowing that, and the current passes through, which is connected in the series. Here is a problem. A particle moves along the x-axis according to the law d square x by dt square plus 6 dx by dt plus 25x is equals to 0 of the particle started at x is equals to 0 with an initial velocity of 12 feet per second. To the left, determine x of t. So this is the example. D square plus 6d plus 25 of x of t is 0. So m square plus 6m plus 25 is equals to 0, where x is equals to 0 and t is equals to 0 is the initial condition. So we will be getting dx by dt as a minus 12 because it is moving to the left of it when the t is 0. So we will be getting m as minus 3 plus or minus 4i. And the x, which is xc actually, but we will be getting as only x because the right hand side function is not equals to any function, that is 0, which is a homogeneous equation. So we get x of t as e to the power minus 3t into c1 cos 4t plus c2 sin 4t. Now that we need to determine the values of C1 and C2 by using the initial conditions what has been given, that is x is equals to 0 when t is equals to 0 and dx by dt will be minus 12 when t is equals to 0. We are taking minus because it is moving to the left, the opposite direction. Before that, when x is 0 and t is equals to 0, we substitute in the solution, that is x is equals to e power minus 3t into c1 cos 4t and c2 sin 4t. When x is 0, the left hand side will be 0, and in the right hand side when we put t is equals to 0, we know that e power 0 is 1 and c1 cos 0 is 1 and sin 0 is 0. Therefore we get a c1 as 0. In order to find the value of C2, we need to differentiate the solution. That is dx by dt. We'll apply the product rule. We get e power minus 3t into derivative of the second part, that we will get it as minus 4 c1 sin 4t plus 4 c2 cos 4t minus 3 e power minus 3t into c1 cos 4t plus c2 sin 4t. That gives on substitution of t is equals to 0 when dx by dt is equals to minus 12, we get minus 12 is equals to 4c2 minus 3c1. And we know that c1 is 0, which we have calculated. Therefore, we get a c2 as minus 12 upon 4, which gives us minus 3. Hence, the solution is x of t is minus e to the power minus 3t into sine of 4t. This is the solution we are getting it. Next, solve the problem of undamped force vibrations of a spring governed by the differential equation m d square y by dx square plus ky is equals to f of t in the case where the forcing function is f of t is equal to a sin omega t, taking the y of 0 as y0 and y dash of 0 as y1. We have here d square y by dt square plus k by m, that is by dividing m throughout, k by m of y is equals to a by m into sin omega t. Let us assume that lambda square is k by m just to simplify, and mu as a by m for convenience. So that our differential equation now reduces to d square plus lambda square of y of t is equals to mu into sin omega t, and the auxiliary equation will be m square plus lambda square is 0. Therefore m is equals to plus or minus I lambda, and we get the yc part as c1 cos lambda t plus c2 sin lambda t, and the yp part is mu into sin omega t by d squared plus lambda square, such that d squared implies minus omega square, and yp is mu sin omega t divided by lambda squared minus w square or omega square, where lambda is not equals to omega, and y is given by yc plus yp. Therefore y of t is c1 cos yt plus c2 sin yt. C1 cos lambda t plus c2 sin lambda t plus mu sin omega t divided by lambda square minus omega square. Also y dash of t is given by, on differentiation, minus lambda c1 sin lambda t plus lambda c2 cos lambda t plus mu into omega cos omega t divided by lambda square minus omega square. This is called that as equation number 1. And now consider y of 0 is y0 and y dash of 0 is y1. So we get y1 and 2 respectively becomes y0 is c1 and y1 is lambda c1 plus mu omega divided by lambda squared minus omega square. Therefore we get c1 is equals to y0 and c2, this on simplification we get 1 upon lambda times of y1 minus mu omega divided by lambda squared minus omega square. So on getting the values of c1 and c2 by using the initial conditions, that is we get y of t as y0 cos lambda t plus 1 by lambda of y1 minus mu omega divided by lambda square minus omega square of sin lambda t plus mu sin omega t divided by lambda square minus omega square. That is y0 cos omega t plus y1 by lambda of sin omega t plus mu by omega lambda square minus omega square of sin omega t minus omega by lambda of sin omega t. And here we need to remember that lambda is not equals to omega. Here is an assignment. The differential equation of a simple pendulum is d square x by dt square plus w square x is equals to e sin nt, where f sin nt, where w and f are constants. If at t is equals to 0 and x is equals to 0, dx by dt is 0. Determine the motion when n is equals to w. And here is the answer for this. Thank you.